Okay, we are now recording. So, apparently always on top doesn't mean always on top. That's interesting. Huh. It's part of always on top. Do you not understand, OBS? Alright, well, let's try this one more time. Click. Nope. We'll do this, and then my video won't cover up the thing anyway. All right, so let's do a code review of imaginary homework and see if we can. We'll just pick somebody at random who's online right now. Let's take a look at Nguyen, no, Singh, Gregorian, Scandin, Thompson, Corrente. Let's pick somebody at random using my random student script. Set 41. All right, Case, not here. Gonzalez, not here. Salazar, not here. Eichmann, not here. Less and less people showing up every day. It's a no. Bomna, nope. Murai, okay. All right, so Lauren and Ishigaki, if you guys can, Maddie, if you can unmute yourselves. There we go. All right, so are both of your turn-ins the same?
Yeah, it should be.
All right, so let's take a look at, so you didn't change imaginary.h, did you? Or did you?
Yeah,
Don't think so.
Okay.
or we added in the
constant.
I think for item complex we added a getter.
Oh, okay.
Okay, yeah, all right. Okay, so what does this line of code here do?
It's basically just setting the R coef to the new coef. Whoever gets the constructor, basically, it gets set to the new coef.
Wait, what is a constructor?
It gets called like automatically when you create a imaginary object for this one.
Yeah. So constructors are functions that get called when a variable is made, and a destructor is called when a variable goes away. Why do you guys not have a destructor?
We're not allocating any memory.
Yeah, you don't need one. You guys are following the rule of zero. The rule of zero is if you don't allocate memory or other resources like network sockets or files or things like that, if you don't own anything, let's say, then you can follow the rule of zero and you just use the default copy constructor, the default assignment operator, the default destructor, which basically all do what you think they do. Like the destructor does nothing, right? Because you're not allocating anything. Okay. So get coefficient returns coefficient, operator minus. All right. So what does operator minus do?
It subtracts them. It subtracts the coefficients.
Okay. So if you have one imaginary number that's 5 and one imaginary number that's 3i, when you subtract them, it gives you 2i, right? What is the difference between these two multiply operators here?
So one is multiplying the coefficient, or one is multiplying an imaginary and a real number, and the other is multiplying two imaginaries.
Mm-hmm.
And two imaginaries is -1.
Mm-hmm. Yeah, very good. And the return values are different, right? So if you multiply an imaginary times an int, you get an imaginary. But if you multiply an imaginary times an imaginary, you get an int, right?
Yeah.
Yeah. Okay. The assignment operator is done for you. And then for the comparison, you're just seeing if the coefficients are the same. So what was the hardest thing? And these were done for you also, right? Or did you have to do these? Okay.
I think so.
Okay. So what was the hardest part of this assignment?
It was
Probably when we were trying to add two, or it'll just work with two different complex numbers, and one could have an imaginary number.
Yeah. Or like there are only
3 terms instead of 4 to work with.
So personally, you didn't need the default constructor for this assignment, but I probably just out of a sense of paranoia would, set them all to 0 or something like that. You know what I mean? And real equals 0 and imagine equals 0, something like that, right? Or if you don't want to, because if you don't have that, it'll leave the real part uninitialized, which is dangerous. It makes me feel a little nervous about it. So I would actually delete it, and then come into complex.h, and rather than using the, you can do this, and so you can actually tell C++, I do not want a default constructor for this class, like this. Okay. It'll make absolutely no difference for your code if I compile this. Use of deleted function. So you were actually making use of it, and so you did have actually uninitialized variables in there. Interesting. So that's why we do that, right? Because your code.
Yeah, you kind of have to if you're not going to use your read library, because you have to declare the complex before you read into it.
Yep. So yeah, it makes me a little nervous having uninitialized variables in there, right? But if you use the read library, you can say complex num1 equals read, right? And then read write. Yeah, so if we come back into complex.h, then we can just do that if you want. But I would personally always make sure that the things are initialized. And you might be like, well, why are you not initializing Imagine then? Well, Imagine has a default constructor, and so it'll default construct itself to be 0, right? I think, right? Yeah. So this would make me feel a little bit happier about the default constructor here. Okay. All right. Get real, get Imagine. You guys added those?
Yeah.
Okay. Yeah, makes sense. No reason not to. Operator plus, operator minus. And so, did you guys do the computer science-y thing of copying and pasting code and changing a plus to a minus?
Yes.
Good. That's literally 90% of computer science is finding somebody else's code that does something similar to what you want and then adapting it to your needs, right? In CSci 45 right now, Muya can verify this is true. I gave them an assignment that doesn't have a makefile. And so I said, look at a makefile from a previous project, because I've given them makefiles before, and adapt it to this one, right? And so, Muya, how hard was that?
Not that bad.
Yeah, but you had to change some things, right? Like you had to change.
Yeah.
Like
for sure.
It wasn't just the file names were different, right?
Yeah, not really, but it wasn't that bad.
Yeah. So.
After you got used to it.
Mm-hmm. Yeah, and so that what I was trying to teach you guys here was that I would give you guys one thing that does work, and then you can use that as a model for adapting it and modifying to get other things that also work. Did you have any trouble writing the multiply function?
Yes, we did originally because we had it in the wrong order.
Mm-hmm.
We had I think when we were trying to do the FOIL, we had the Imagine on one side wrong, so we were getting an error for that, but then we were able to fix that.
Yep. And so that was actually one of the main things that I wanted you guys to learn from this assignment, was that if you have an operator like this, if it's a member function of a class, me must be the left-hand side, right? So my real, me is the left side of the multiply, and so you could do this. You can multiply an imaginary times a real, But you can't multiply a real times an imaginary, because in that case the imaginary is on the right hand side. And so if you wanted to be able to do that in the opposite order, you'd have to use a free function that would take a real on the left hand side and an imaginary on the right hand side. And so a lot of programmers will do both versions, and it's just kind of very verbose and tedious and time consuming. And so getting used to maybe these kinds of restraints is a good thing to get used to, right? Where your class has to be on the left hand side, or maybe it's not. I don't know. Maybe it's unintuitive, and you'd want to add a multiply operator that works both ways. Okay, so foil. So yeah, you're foiling it, and then you are doing that, right? So that's the first. That is the outside inside and last. Yeah, okay, you got all four things in here. And then you put them together into a new complex number and return it. And one thing you could do if you want to have less verbosity is you could do this, right? You understand what's happening here, Lauren and Maddie?
Yeah.
Yeah.
So we're making it an anonymous variable, right? It will convert from this into a complex when you return it. So you can just do it that way if you want to.
It kind of started out that way, but then as it evolved and we kept making mistakes, it eventually became more complicated.
Mm-hmm. Yeah, and the way you did it has one really big advantage, which is that you can see out the return value, right? So if you want to find out if your code's working, you can do this, right?
Mm-hmm.
And then when you're done with it, you're like, all right, comment it out or delete it or whatever. Okay, double equals operator just compares the two parts. That's cool. How was exponentiation for you guys?
A little bit of a mess.
Yeah. Temp real, imaginary real, imagine multiply, temp equals real, imaginary temp 3 equals imagine. Okay, all right. So you're actually doing the foiling again here, huh? Yeah, you didn't need to go to this level of detail. You could have just used your multiply operator, right? So.
Oh yeah, we kind of copy and pasted it in there.
Yeah, that's fair. That's fair. But some of the point of using a function is that you don't have to copy and paste code, right? You just call your function. And so my exponentiation just has the complex numbers multiplying over and over again. It's just repeated multiplication. There's better ways of doing exponentiation than that. You can actually do it in order log base 2 in time rather than order n time, but none of the problems for the homework assignment mattered for that. The numbers you'd get would be absurdly big anyway. If you had a giant exponent. All right, so if exponent equals 0, you just return 10. Otherwise, you return that. Okay, yeah. Okay, yeah, looks good. And then double left arrow, double right arrow. And then the thing that I'm sure everybody wants to see, which is the main. So let's see, you read in a complex number, you read in the operator. If the complex number was bad, you die. If they typed in 00, you quit with success being passed back to the operating system, which isn't used by anything, but it's a good habit. Good job there. You then look at the operator, and if the operator is everything but exponentiation, if the operator is anything but exponentiation, then you read in a second number. What I did was I actually checked for this first. And if it was exponentiation, I handled it. Otherwise, I did this, so that you see how you guys repeated these two lines over and over again. So I just did that first, and then after that, I knew I had to read a second complex number in, so I didn't have to copy paste quite so much. But this works fine. Did this remind you of the calculator assignment we did in 40 at all? Did we do the calculator assignment in 40?
Yeah, we did. I just don't remember it that well. It was just calculating.
Yeah, you do plus, and then you do the plus, and
Yeah, okay.
minus, you do the minus, and if it's times, you do the times. But the whole point of like all this class stuff we're doing is that you can actually write code like this, right? Where you can just, take the result and have it equal to a complex number times a complex number, right? And these complex numbers you may just behave like you think they should, right?
Mm-hmm.
Yeah. So here, true or false. What you can do here instead of doing this is you could do this instead. Cout bool alpha, which rather than outputting 1 or 0, it'll output true or false. And then you could say if num1 equals num2. And a lot of times when doing these things with a cout statement, you want to put them within parentheses, because there is an order of operations problem that comes about from the heritage of C. So the C language uses double left arrow as a bit shift operator. So it takes all the bits in the number and shifts them left like 1 time or 10 times or whatever. And C++ was like, it's a cool idea to reuse the bit shift operator to output things. And so it doesn't behave the way that it should because C++ couldn't change the order of operations of things. And so what happens is that if you don't put parentheses around the quantities you're trying to see out, then a lot of times it won't compile, right? So like, I think it'll work with plus and minus and things like that. With double equals, I think it doesn't work, and with exponentiation, it definitely doesn't work. And so if you were to try to like, if you're going to try to do this, cout num1 exponent, like that. If you try compiling this, then it won't compile, right? So you have to wrap this in parentheses. So just as a general rule of thumb, like rather than trying to remember like which ones work, plus works, but like I tend to just put things within parentheses and it compiles fine, right? So as just a general rule of thumb, I tend to wrap any expression in parentheses when I'm couting them, okay? Because it parses really weirdly. Like the compiler is not an error, it's not a bug, it's just a legacy thing from the 1970s where they said this is a bit shift operator, and so the please excuse my dear Aunt Sally, that whole thing. It just creates weird results. But P, please, is the top. So you just put parentheses around the quantities and it works fine. Okay, well done. Everyone, please give a round of applause for the Murai Ishigaki duo. Well done, well done. Very good code. Excellent job. Okay, so we are going to talk a little bit more about Big O today, because Big O is really, really important in computer science. It's every time you look at a reference page, it'll typically have is putty floating on top? Is that why it's covering up everything? Why is putty floating on top? How is putty floating on top? This doesn't even make sense. Weird, I can't bring my browser in front of putty. What the hell is going on here? Huh. Okay, well, so cppreference.com should be a website you got bookmarked and check it every day. I mean, not really, but it's basically the go-to place to look up things about C++. And I use it all the time when I want to figure out how to find something from a string or whatever. Like, I'll just come here and be like, all right, strings library, let's click on that. All right. And, all right, so documentation. Okay, that's cool. All right. Click on that. And then I can scroll through here and see all the different things I can do with a string. And you can erase characters and push and pop characters off of it. And, oh, look, here's a bunch of find functions, right? Find characters in a string, find the last occurrence of a substring within a string, find the first not in it. And so, and let's just say, let's go to find. And if you click on that, then it tells you all the different operator, all the function overloads, which it looks like there's 5 different ones, 5 different ways you can call find on a string. And this looks like hot garbage, right? So usually I just scroll down to the bottom here and like, oh, there's actually code. That's nice. And so let's look at main. So we've created a constant string called this is a string, and it's going to find is. So it's going to try and find is within that. And then it's going to call this print function. What does print do? Let's look at that. So it takes a size, okay, and a string. Oh, I should have clicked on that. And so it's going to print starting at n, I think. Yeah, found. Then it prints starting at n, that word. And then you can run it. So you can actually click run, and it'll actually copy and paste the code into Colaru, which is an online compiler. And you can actually edit the code right there and hit run on it, and it'll think for a little second, and then it'll print the output down here. And so you can see this is how you can search through a string to find other strings. Cool. And you guys are more than welcome to copy and paste from here. It is not plagiarism. It is a reference. Okay. So if you ever want to just 100% plagiarize anything you find on cppreference.com, go for it. I am not going to bust you for using the reference manual. Okay. So this is an exception to the rule. Normally if you ever find yourself hitting Control-C, Control-V, or the PuTTY equivalent of Shift Insert for paste and Control Insert for copy, normally it's bad, and the cheat detector we had picked up a lot of similarities on the last homework assignment, but fortunately it was a partnered assignment, so it was actually detecting the partners, right? Although sometimes there was groups of 3 apparently, so I need to go through those with a fine-tooth comb and find out if some group had a unofficial 3rd member, which would be cheating in it. Okay, so but you can plagiarize, so to speak, from CPP reference, cppplagiarism.com. There's so much info on CPP reference, I get lost. Yeah, exactly. So basically, when you look at this kind of thing, it's like, like it's just, there's pointers, and it's just this, horrible block of things in front of you. And so usually I just scroll down and just look at how they actually find something. Okay, and the examples are usually pretty straightforward, right? So it's going to be looking for the word is inside of a string. This is going to be searching from position 5 onwards, which should still find it. Finding a letter, right? So this is if it finds a letter. This is if it doesn't find a letter. So if it doesn't find something, it returns npos. And so if all you did was like look at the documentation, like this, right? Constants, npos, special value. The exact meaning depends on the context. That doesn't tell me anything, right? And so, like, you great. The exact meaning, what is the exact meaning, right? And usually what the meaning of npos is means you didn't find it, right? It's not in this string. So if you say what location in the string is the word Bob, and Bob's not in the string, then it returns npos, which means essentially not found, right? And it's max int, technically, max unsigned integer. So so if you're finding things and it returns npos, that means it was not found. No position found, I think is what it stands for. It generally is used as an end of string indicator or an error, meaning that it couldn't find something. Okay. So basically, anytime you search for something, it will return npos if it can't find it. Okay. And so looking at the example code, everything makes sense if you read the documentation. This is a special value equal to the maximum value represented by the size underscore type. The exact meaning depends on context. Like, yeah, that doesn't help, right? But when you look at their source code examples, like, okay, all right, cool, and then you can just plagiarize freely. It's free. They give you permission. Okay. So C++.com uses namespace, so probably, yeah. Yeah, they normally will. Let's check this one out. Yeah, they normally don't use namespace standard, right? So here they do it the proper way of putting STDs everywhere. Okay. They love themselves some STDs. All right. So, yeah. So CPP reference, great. Great reference. Now, what I was getting at, C++ 23. We are living in the future. We are living in the future. Look at this. Nice. C++ 23. Nice. Cool. Is that approved already? That's awesome. Makes me happy. People think there's still going to be a future in 2023. We're all going to be alive by then. But now, what I actually wanted to show you today was let's see, containers library, vector erase. Okay. So when we talk about Big O, we talk about time complexity and space complexity. So time complexity means how long something takes to run, and space complexity means how much RAM does it take up. Okay? So it's basically running time versus RAM, right? The cost of an algorithm. And every algorithm usually has a cost. You'll find very few order 0 algorithms out there, right? If you try to sort something that's already sorted, maybe it's order 0. You know. But usually there's a cost to, like, was it sorted? You have to check, right? So to delete something from, as long as the references are from these specific sites, we will not be marked down for plagiarism. That is correct. You are free to plagiarize from cppreference.com, and I'll even give you c++.com also, though I don't recommend it. You can freely plagiarize from them. I don't care. Okay, so, because, I mean, that's literally what professional programmers do. We have cppreference.com bookmarked, and there's plugins you can use so you can even access the site when you're offline, right? Like, it's that important to us. Or you can install man pages on the server. So what is important, though, is this. So when it says linear complexity, then what that means is the amount of time it takes to erase something from a vector. Worst case, these things we always think of them, 99% of the time we think of them as worst case scenarios, right? So if you're going to erase something from a vector, and when you erase something from a vector, you have to move all the elements that are to the right of you one spot to the left, so there's no gap. You can't have a gap in a vector. So if you erase something from a vector, then worst case scenario, you're erasing the first thing in it, and you have to move, essentially n elements to the left. N is always the size of the vector, or whatever operation you're trying to do. So number of calls to the destructor of t is the same as the number of elements erased. The assignment operator is called the number of times equal to the number of elements after the erased. Yeah. So if you're deleting n objects, then it's going to call n destructors, right? Because the destructor gets called implicitly every time you destroy something. So if you're going to be destroying 50 things from a vector using erase, then you've got to call the destructor 50 times. And then if you have another billion elements in the vector, you have to call the assignment operator, which is the equals operator. You have to call that 1 billion minus 50 times. And so you're going to be doing n work, where n is the size of the vector. So this kind of thing is part of the common parlance, the common terminology, the shared lingo and jargon that identifies you as a member of the cool kids group, the N group. Like every group out there, in every professional organization or association, or even if it's informal, like just the group of all teachers in America, or the group of all school administrators, or the group of all counselors, all of them have their own in-group lingo, in-group terminology. And I'm not a fan of terminology and lingo and things like that. I like using really basic English words that anyone can understand, like parlance. But you got to know this one. You got to know this one because this will mark you as a member of the, programmers club, right? And so when programmers are talking, they're like, hey, how long does that program take to run? We usually don't refer to it in terms of numbers unless we're actually benchmarking. Like, oh, that took 50 milliseconds. Usually when we're talking about your program, like, hey, how fast is that algorithm you just wrote? I would say, oh, it's order n squared. Oh, okay. Is it too slow? Nah, it's all right for now. I only have to run it once a week and it takes 10 minutes. It's not really worth my time to fix. Yeah, okay. I'm like, I could get it down to order in log in time, but yeah, I run it once every week, and it's 10 minutes, and it's just not slow enough to bother me. Okay, all right. And that's just a normal conversation that programmers will have, because there's programmer time that you optimize your time, and then you optimize the running time of the computer. For example, when I grade your homework, it runs your program on each of the test cases, and then it runs my program on each of the test cases and compares the output. Now, there's a very obvious optimization there, which is that I could save the results of my compilation and only run my reference implementation once, right? If I have n students in the class, I am doing order n work running the reference implementation rather than order one. I really should just run my program once, save the results for each of the test cases, and then compare that against yours. And I don't, because there are sometimes test cases that are based on the current time. At least that's what I tell myself. In reality, I don't use those test cases. And so really it's just, it would take 20, 30 minutes of my time. And the reality of the situation is the input tester is fast enough. And it does take like a minute or two to grade your homework. And so, you know, I could probably speed that up by a factor of 2. Right now I've got 2 order in operations. One, it runs in students code, and one, it runs my reference implementation n times. And I could easily change that from order n to order 1, but it's fast enough that it doesn't bother me. Most of the time spent in the auto grader actually is spent with students whose code hangs. So if your code goes into an infinite loop, my auto grader is actually fairly tolerant, and it'll give you like 5 seconds for your code to just sit there and spin endlessly, and then it will kill it. And then that's one test case. So if there's 20 test cases, then it's running for 100 seconds to grade one student who has an infinite loop. And so that's, you know, and so my code runs like that. It's really not, it's not something I really worry about, you know. So, but that would be an example of a conversation, right? My code is running in order in time. I don't say it takes 5 seconds or 10 seconds. I say it takes order in time. And I could get it down to order 1 time, constant running time. It would run 1 time and save the results. Okay. Order 1 doesn't just mean fast. It means that as there are more and more students in the class, I wouldn't need to run my reference implementation more than once if I did it properly, right? But right now, my reference implementation runs n times, where n is the number of students in the class. And so right now, the running time of my reference program is order n, and it could be order 1, right? So yeah, if you look at the CPP reference, it will tell you what the complexity is of these different operations. So pushback is kind of constant running time, but it's actually what's called amortized constant running time. So let's see if we can find it. There we go. Complexity is amortized, amortized constant running time. What is amortized? Amortized. Isn't that like a almond flavored liqueur or something like that? No, that's amaretto. What's amortized? What does that mean? Anyone here, an accountant or a mortgage broker? Aromatic. Takes longer. Yeah, so this is a learning point for today. Okay. So as it turns out, if you push a million elements into a vector, it will take, on average, 1 million operations. Okay. But or some constant number of operations, let's say. It doesn't, the cost of pushing something back into the vector doesn't grow. Like the bigger and bigger a vector gets, you would think, you know, if you were inserting at the beginning, if you were going to insert at the beginning of a vector of a size 1 billion, you would have to make room. You'd have to move 1 billion elements one to the right. It would be an order in insertion. But for pushback, all you do is you grow the array at the end. Now, as it turns out, growing arrays isn't like actually a thing. What happens is a vector behind the scenes has an array. And usually this array is twice as big as what you need. And so as the array fills up, pushback, 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 order 1 time, order 1 time, order 1 time. It just has a pointer. Remember, it's got an end pointer. It just got a pointer to the end of the array. And And that's why it returned 0 last time, right? Was because I outputted the value of end, but it actually is secretly in bounds because the vectors will usually over allocate memory by a factor of 2, or it's not, I think, set in stone, but it's usually like a factor of 2. And so it fills, and then when it runs out of room, the next time you do a pushback, it doubles the size, it allocates a new array twice as big as before. It copies every element over, which is an order in operation. So you're like, wait, this isn't order in, but it's on average order 1, right? Or you'd say this isn't order 1. Some of the time it'll be an order in operation, yes, but it is an order in operation once every n operations. So it's like saying a tenth of the time you have to do 10 operations, right? So that's actually amortized constant running time. On average, it is constant running time. And as the array doubles in size and doubles in size and doubles in size, the number of times you have to reallocate becomes less and less, but the cost grows more and more. So if you actually plot the running time of pushback, as you're inserting elements, it'll have a constant running time, and then it'll spike. And it'll be constant running time, and then the spike will spike even harder. Spike even harder. And so there's a function in the standard library called reserve, and reserve will actually tell C++, hey, I'm planning on storing about 1 million elements in here. And so what it'll do is it'll reserve secretly behind the scenes a block of 1 million elements, or maybe 2 million elements. They usually they waste memory, right? So it might allocate 2 million, or it might allocate a factor of 2. You don't really know. But it'll allocate usually at least 1 million elements. And then as you push back into it, then it doesn't have to do those reallocations every so often. So so pushback is not constant running time, it is amortized constant running time. So if 1/10 of the time you have to do 10 operations, that works out to, on average, if 1 out of n times you have to do n operations, that actually works out, mathematically speaking, to constant running time, right? 1 out of every 200 times I have to do 200 operations. That works out to 1, right? So, yeah, so it's not constant though. Like if you plot the running time of each of your pushbacks, there'll be these spikes, and that can actually be quite brutal, right? If you're in a video game and you've got a vector that's got 300 megabytes of RAM in it, and you trigger a reallocation in the middle of your game, the game will pause while it allocates 600 megabytes of RAM and very dutifully copies over 300 million bytes of data, and so you'll have a hitch. The game will pause for like a second, and then it will continue, and then it'll be fine for a while, and then it'll pause even longer as it hits the 1.2 gigabyte memory, copies things over, and then it'll pause even worse as it copies 2.4 gigs of memory over, assuming the vector just keeps growing and growing without bounds. And so you want to use reserve if you know in advance how much you're going to need, because that avoids those frame rate hitches and uneven running times and things like that. The new Modern Warfare had an issue at launch where you respawn the entire game, which just pause sometimes. Yeah, pretty common, right? Or anytime you go into a new area, it's got to load stuff off disk. If there's new textures, it hitches while it loads the textures. The game just pauses. It's a problem. It's a problem. Yeah. So you do what you can to stop them. Okay. So shrink to fit is the opposite of reserve. Basically, if you've added a lot of things to a vector and then you've deleted a lot out, you can call shrink to fit, and then the amount of memory used will shrink down as well. So if you don't need as much memory anymore, shrink to fit will basically free up a lot of the memory. Okay. It doesn't have to, I don't think. Yeah. I don't think it has to do it. Like reserve, I think, can be ignored also. Reserve does not change the size of the vector. Capacity. I don't know if it. Maybe it must do reserve, but I seem to recall it being sort of implementation specific what it actually does. Okay, so yeah, CPP reference, super useful. And then for basically all of these operations, you can be like, all right, well, you know, what's the running time on it, right? And so if you if you resize a vector, then it will take linear running time. It will take order n running time. Okay, so let's do some examples of order n analysis on the server. Okay. And Putty is still pinned. I don't know what's happening. Why is Putty on top of all the other windows? How did I do this? It's black magic, dude. All right. Nope. It's not that. I don't know. Okay. Try restarting it? Sure. Okay. Is there an always on top option? Oh, there you go. Okay. Okay. Weird. All right, so let's take a look at main.cc. Let's get rid of it. Okay. Int main. While true. The vector of int named vec. Vec dot push back read. If vec dot back. Let's see, was it? Is it back? Yeah, it is back. Okay. Equals 0. Then vec dot pop back, delete it, and break. Okay. All right, so this will read integers from the keyboard, and then let's print them out. For every integer in the vector, see it out. Okay. Four, 3, 2, 1, 6, 7, 8, 9, and 0. So you can see we got 4, 3, 2, 1, 6, 7, 8, 9, and the 0 gets discarded because the 0 means end of input. Okay. Why is there no return 0 in main? Great question. Every function in C++ must have a return value except main. Main promises that it returns an integer. However, in the official standard, and a lot of people don't know this, including the people at CPPCon, and I know this because I learned it at CPPCon during one of their trivia things, like, did you know? And I was like, oh, I did not know that. Because up until then, I'd always been very dutifully putting return 0 here. As it turns out, if you omit return 0, it'll put it in for you. So there you go. But you can't do that. You can't do that anywhere else. So if you have int foo or whatever, you can't just like do that. It will be mad at you, right? Non-void function does not return a value, all right? So you gotta return something, all right? Technically, you could get away with not returning something, and it'll probably crash your program if you don't. It's actually really, really bad to not return something when you say you're going to return something. Like if you say you're going to return a string and you don't, and then it treats the whatever random memory on the stack as your return value, and it jumps to that location, and it'll probably segfault your program immediately. You really, really, really want to always return something from function, except main. You don't have to. It's part of the standard. You don't need to. You don't need to return 0. Okay, so what's the reason? Convenience, I think. It's just convenient. You know, not all operating systems even use error codes, and so why make somebody do something for the Unix operating system when other operating systems don't necessarily require it? Okay, so right. So how long does this code take? How long does this code take to run? What do you guys think? What do you guys think? How long does this line of code right here take to run? If I've got a billion elements, in the vector, will this for loop take longer to run than if I have 2? Yes, right? Because it's got to output this a billion times. So if you have 1 million people in VEC, it will do 1 million cout statements. If you've got 1 billion people in VEC, it'll do 1 billion cout statements. So this is a classic order n algorithm. Okay. What about this? Let's say I want to check for duplicates. Okay. I guess we can make a function for check for duplicates. Cout bool alpha check for duplicates, and I'll pass them back to it by an inline. And so it's complaining you haven't written check for duplicates yet, and that's absolutely right. So we're going to write a function that returns a Boolean and is named check for duplicates. Thank you, Cock, for filling that in for me. And we will take in a const vector of ints by reference named vec. Very convenient to have every vector named vec, I guess. And it should be a lowercase v. Thank you. And let's just do this. So for size t I equals 0, I is less than vector dot size I plus plus. For size t j equals 0, j is also less than vector dot size j plus plus. If I and j are not the same, because obviously what we're going to be doing is we're going to be saying for every element in vector, check every other element in the vector. And so if you were to check the same one, it would be a duplicate, right? We don't want that. So if I is not equal to j, in other words, if we're looking at two different elements in the vector, if I is not equal to j, then if vector square bracket I, because I know it's within bounds. Here, let's just use at for you guys. You technically don't need to use at here because we know it's within bounds. This construction here will guarantee it's within bounds. So yeah, sure, I'll just use square brackets. If vector square bracket I is equal to vector square bracket j, then we will return true. There is a duplicate. And if we get through this entire loop, without finding a single duplicate, well, then guess what? We can return false. There were no duplicates. So, what is the command code to install Cock? It is technically in your vimrc file. If you can figure out how to install it, you can be rewarded with Cock. So, I will not, however, teach you how to install it. It is an Easter egg for dedicated students to find. Name is unfortunate also, by the way. I apologize. But that's his name. So for int I equals 0, I is less than vector dot size. For size t, j equals 0, j is less than vector dot size. If I is not equal to j, so we're basically saying for every element in the vector, for every other element in the vector, if they're the same, return true. We have found a duplicate. Otherwise, return false. Okay, so if the vector is of size 1 billion, this for loop will run 1 billion times, right? And for each time that loop runs, it'll run 1 billion times. All right, so the total number of times the inner part here runs will be 1 billion times 1 billion, which is, I don't know, a large number. Okay. So we can annotate this. Order n squared. Order n squared. How long does an if statement take to run? Is that order n? No, sorry, not order n squared. Sorry, leaping ahead to the answer here. How many operations is an if statement? Is this proportional to the size of the vector, or is it constant running time? Very good, very good. It is constant running time. Okay. How long does it take to do a comparison? Does this comparison, comparing one element with one element, is that proportional to the size of the vector, or does it take the same amount of time? that is also order 1. Okay, so this line of code right here is also order 1. It does not take longer to compare element 5 with element 7 if there are a billion elements or if there's 10, right? Because this leaps to a spot in the vector immediately. This leaps to a different spot in the vector, and it compares the two of them, and it doesn't matter how big the vector is. That line of code right there takes one operation, we'll say. Yep. Technically, there's like a multiply and an add and a multiply and an add and a comparison, but it's a constant amount of running time. Order 1 doesn't mean you're doing one thing. It means constant running time. The amount of time it takes to compare one integer with another integer is constant. It doesn't, like if the vector is big, if the vector is small, this line here will always take the same amount of time. It doesn't matter. And grabbing one element out of the vector and comparing it against another element out of the vector is also constant running time. It will take the same amount of time whether the vector is big or if the vector is small. Okay. What about returning true? Does return true take longer if the vector is big, or is it always the same amount of time? Is constant always equal to 1 value? Yes. And the reason for that is because when we're talking about big O, we don't care about fiddling details like, is it order 1, order 2? In this case, this would technically probably be order 5, because a square bracket is it grabs the pointer's address and then it adds the offset to it, but it has to multiply the size of the type, in this case int, 4 times I plus the memory location of vector's internal array. So it's a multiply and an add, and then for this part here, it's a multiply and an add, and then it's going to compare the two of them. So like I said, it's technically like probably 5 operations, but we don't care, right? What we care about is the shape. We care about the shape of the curve, right? We don't care, let's say we did this twice. Like let's say we did I is less than 2 times vector.size. This would still be order n. Even though you're like, wait, isn't that order 2n? Yeah, it is, because it's now doing twice as much. It's like if it's a vector of size 1,000,000, this would do 2,000,000 iterations. But we don't care about fiddly things like that, like twice as fast. We don't care. We don't care. So even if it was this, even if it was like 20 times the size of the vector, that is still order n. It is a linear curve, shape, linear relationship. It's a linear relationship between the size of the vector and the amount of time it takes. We don't care. So whenever you talk about big O, there is this notion, like if you say order n, that means that there is some constant times n, basically, that bounds the time that is going to be greater than the amount of time it takes to run. And so there is some k that that will bound it from above, is what big O means. And so we don't actually write the k down, because what we care about is that it has a linear shape, right? So if you had an order n squared algorithm, you can't bound an order n squared algorithm with a line, because at some point the n squared is going to exceed the line. And so for all values of n, there is a k that will bound it from above, is the technical mathematical definition of it. But basically, your options are constant running time, which is order 1, linear running time, which is order n, quadratic running time, order n squared, that kind of thing.
What was that weird algorithm that had like order log n squared log whatever?
Yeah. Just last week I was looking at one that was order n log n. Yeah, there's like Shor's algorithm. So the running time.
Shor's algorithm, that's it.
Yeah, you're gonna like make them not want to learn big O after looking at this, but it's order log n squared times log n times log n. So that's a champion running time right there. And this one is order e to the 1.9th power times log of n to the 3rd power times log n to the 2/3 power, right? Like, I would be terrified of the proof of that. I would be absolutely terrified of the proof of that algorithm. So you don't need much math in order to code. You don't. Like, the people that do algorithm analysis are typically more math people. Programmers work with this, okay? And so the amount of time it takes to compute check for duplicates is what? The total amount of time for this algorithm. So toss it out in chat and I'll start walking through it in English. So if you've got a vector of size 1 billion, this outer loop will run 1 billion times. For each iteration of that 1 billion times, it will run 1 billion times. So that is 1 billion times 1 billion times. It will do 1, 2 operations, let's say. So it's 1 billion times 1 billion times 2, let's say. Okay. 1 billion times 1 billion. You can't do the return 1 billion times because it'll return, right? So there's kind of no, you know, you can't return true 1 billion times. You can return true once. So the total running time of this is what? How would you describe in Big O, what is the running time of this algorithm? I.e. the time complexity. Okay. After the first billion, then I becomes 1. Then it does another billion, and then I becomes 2. And does another billion, and I becomes 3. So 1 billion times, it'll do 1 billion times. Yes, it is a quadratic algorithm, or order n squared. Very good, team. And so, let's just see if this works. So order n squared is not great. It's not terrible. It's not the end of the world. 1, 2, 3, 4, 5, 6, 7, 8, 9, 89, 10, 0. No duplicates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. There is a duplicate. So there you go. Like, so for 10 inputs, it had to do 100 comparisons. This computer runs at however many billions of times a second. Like, you're not going to notice it for small problem sizes. So have an order 2 to the n algorithm. Just force the size of the data set to be constant. Yeah. Good. You've been reading the Zybooks. Excellent. Excellent. Good. So the what if we did I don't know. What if we did this? What's the running time of the algorithm now? I don't think the correctness has changed at all, actually. That K is completely pointless, but it'll compile, it'll run. What do you guys think? Reminds you of linear algebra. It's way easier than linear algebra. It's just, the secret here is when it's nested like this, for each time, for n times, do n things. For each of those times, do n things. For each of those n things, do one thing. For each of those one things, do one thing. You just multiply your way down. All right. So if they're nested like that, you just multiply them. Okay. So yes, you guys have it. This is order n cubed now. Okay. Now, what if what is the running time of this algorithm now? What is the running time of check for duplicates now? Order what? It's no longer nested, right? It's no longer nested. So you're going to do the upper loop first, then you're going to do the lower loop second. Worst case scenario, there's no duplicates, so it doesn't bail out early. Remember, you always have to think of this in worst case terms. So it doesn't find any duplicates. It doesn't, because best case scenario, the very first pair you check are duplicates and it returns, right? You don't care about that. You always have to think about it in worst case time. So it's going to do n squared. This whole thing here is n squared work. Then it does n work. So what is the running time? The running time, you might think, would be order n squared plus n, right? And technically that's correct. Nobody's really gonna. I mean, it's kind of wrong, but it's correct, right? It's technically correct, the best kind of correct. And why it's correct is because you're doing n squared work followed by n work. Here's the thing, though. The n squared grows so much faster than the n, right? That we usually just omit terms that are dwarfed by the bigger term, right? If you remember big O is, there's a bounding, so there's some k times n squared that will be bigger than the function past some point, is the mathematical definition. The plus actually will get dwarfed by the n squared. And so mathematically speaking, you don't need to write the plus at all. I mean, think about it. If you've got a million elements in this vector, you would do a million times a million comparisons here, and then it would do one more million here. So it's the difference of a million and one or a million, right? So nobody cares if it's a million and one versus a million. Like, we don't care. Like, literally, we just don't care. It's for any size of any consequence, the n squared will be so much bigger than the n. We just literally don't care about it, right? If you've got 100 elements in the vector, which isn't even that big, right? 100 times 100 is 10,000, and so whether it's 10,000 or 10,000 and 100, it's a difference of 1%, right? Like, nobody cares, right? And as it gets bigger, the difference, the significance of this drops immensely. So, yeah, n squared plus n, you could write it that way. It's kind of a newbie thing to do. Just kind of like some people would write like order 5 here, which technically you can do. You could technically write that, but it's kind of a noobish thing to do, because for order 1, remember order 1 means there's some k times n, right? And so 5 could be the k, right? So you don't need to write order 5. You just write order 1. And that's typically what we write. Or we write it in English, like what we saw on CPP reference, constant running time, or sometimes amortized constant running time. It's a little bit different. Order n is called linear running time. Order n squared is quadratic running time. And then you've got bad ones. The bad ones look the same as the good ones, right? But this is exponential running time, and this is super duper bad. Let's just say super bad. It's really bad. And then there's order n factorial, which is called factorial running time, which is ultra, I'll just say super duper bad running time. And then there's even worse ones that are extraordinarily bad and things like that. But basically, algorithms above this are said to be in p time. Below is np time. And so p means polynomial time. You can represent it in a polynomial, x squared, x cubed, x to the 4th. All of those are faster than np, non-polynomial ones, right? Which are exponential running time or factorial running time. Always take the highest magnitude number of the exponent. Yeah, like little fiddly details like, is it 2 times n squared? We don't care. We don't care if it's 2 times n squared. We care if it's n squared or n cubed, right? N squared or n cubed, you would write down, like if it was n cubed plus n squared time, you'd write down n cubed. You always take the biggest term, right? So, so exponential running time is generally considered to be unsolvable. So if you have any program of any size like that matters, like you can solve a 2 to the n algorithm, if you've got 3 cities, right? 2 to the third power is 8. It's not that bad, right? It's, you know, it's actually faster than 3 squared, right? 9, right? So for 3 cities, the exponential algorithm is actually faster, right? 2 to the third, 2, 4, 8, whereas 3 squared is 9, right? So quadratic's worse. No, exponential is way worse. It's way worse. By the time you get to like 100, right? 100 squared is 10,000. 2 to the 100th power is more than the atoms in the universe by quite a large factor, right? Exponential becomes intractable, unsolvable very, very quickly. So for very small numbers, you can actually write an algorithm that is exponential and will run for very small numbers of input. But, you know, if you want to solve the traveling salesman problem is one in which you visit. You have a bunch of cities in America, and you have to visit them and try to minimize the total distance you travel. You visit each city once, and you try to make a circuit around America, and it's a order 2 to the n algorithm. And so you can directly solve it if there's 10 cities, you know, 2 to the 10th power is 1,000, whatever. But by the time you get to like 50 cities, it's unsolvable. And that's still a very small number of cities, right? So, you know, and if you can solve it for 50, barely, then 51 is twice as hard. And 52 is even twice as hard as 51. And by the time you're talking about 60, it's like, forget about it, you know. Talking about years, and then 61 would be twice as many years, and it gets really bad really fast. So an example of a factorial algorithm would be brute force shuffling or sorting, let's say. So let's say you have a shuffled deck of cards and you want to sort them by face value and suit, right? So one way you could sort the deck of cards is to randomly shuffle it and see if it's sorted, right? And if it's not, shuffle it again, right? Try a different shuffle this time. Shuffle it again and see if it's sorted. That didn't work, try a different shuffle. Shuffle it again. Shuffle it again. And just keep randomly shuffling this deck over and over again, trying a different shuffle every time until it happens to be sorted. 1 ace through king, ace through king, ace through king, ace through king. And so that is an order in factorial algorithm. It's an incredibly inefficient way of sorting something. In traveling salesman problem has been solved recently. There are solutions for the traveling salesman that are based on certain assumptions, like a Euclidean plane and stuff like that. But there's no full solution to it. There's lots of approximations to it and things like that. So so a factorial algorithm is like really bad, right? It's even worse than exponential, right? Because exponential is 2 times 2 times 2 times 2 times 2. Factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7. So factorial is even worse, right, than exponential. So then the opposite. So as bad as exponential is, that's how good log is, right? So log, which is order log n, is called logarithmic running time. A log n, like, people don't really have a good grasp on how long log n takes, but log is the inverse of exponentiation, right? So a logarithm, if you think back to 8th grade or whenever it was you took algebra 2, a logarithm is the opposite of an exponentiation. And so for a logarithmic algorithm, for every doubling of the problem size, you have to do one more step of work, right? So if you're trying to search for a name in a phone book, what you do is you open it halfway, right? Do you guys know what phone books are? Right? Let's say you're trying to find a name in a phone book, and you want to find Muya, right? So you open it up halfway, and that's, let's say, the K section. And you're like, okay, M, I'm looking for Muya, so M is to the right of K. All right, so you ignore the left, you throw away essentially half the phone book, right? You know it's not to the left. You can rip the phone book in half and throw away the left half. You've searched essentially through that entire half of the phone book with one step. You open it up halfway, and you're like, okay, M is to the right. So you can throw away everything to the left. And then you repeat. So you open up the phone book to the middle again. Oh, I'm in the N section. Okay, well, M is to the left over here. So you can virtually rip out the right half of the remaining phone book, throw that away. You open it up to the middle. We're in the MO section. Okay, well, Muya is let's see, to the right of that. And so you rip it out and throw the left half away. So with every step, you throw away half the phone book. And so if you were to, say, double the number of people in Fresno, and you would go from, what is it, about 1 million people in the greater area. If you go from like 1 million people to 2 million people, you only have to do one more step. Is Muya in the left phone book or is it in the right phone book? It's in the left one. Okay, throw away the right one. And so you just got rid of 1 million new names with one step. So logarithmic running time is fast. It is really, really fast. As super bad as exponential running time is, logarithmic running time is super fast. Okay, it's not as fast as constant running time, but it is super fast, right? And usually this is kind of the overall you usually can't beat linear at a certain level because you have to process the data, right? So like if you're going to be searching for names in a phone book, the first step you have to do is load the phone book into memory, right? And so from a certain sense, order n is kind of the baseline overall for your whole program, because when the program launches, it's going to have to load all the names from the phone book into disk. But then every search you make after that will be done in order log in time. So, so basically any algorithm that runs in order n time, you can think of it as being free, because you can kind of do it at the same time you're loading the names, right? So if I'm trying to find the person with the longest last name in Fresno, I could actually do it as I'm loading the names. Does that make sense to you guys? Right? Does that make sense? Like, let's say I'm interested in whoever has the longest name in Fresno. When I launch the program and I'm loading all the names from disk, I can just sit there and be like, okay, well, Muya is 4. Okay. Oh, we've discovered Pata. That's 5. Okay, get rid of Pata, or get rid of Muya. Say Pata. Oh, we've come across Edrelin. Well, Edrelin is 7. Okay, so throw Pata away, write down Edrelin. And so just as you're just reading through the phone book, you can just sit there and kind of keep track of whoever has the longest name. And at the end of it, you can be like, all right, whoever has the longest name is the longest name, right? And so you can almost think of linear algorithms as free, if there's something that can be done while you're loading the data set, because you can't get around loading the data set, right? Like, you're gonna have to look at the names at least once, right? But once everything is loaded, then that opens up. Once things are loaded off disk, then that opens up constant running time, logarithmic running time, algorithms like binary search, which I just described, or phone book search, right? Where you can make search after search after search after search in login time, and it's very, very fast. So the short example you shown on Wikipedia is really fast. I don't know, man. It's like I don't really have an intuition on what happens when you multiply those many things together. Sorry. my poor brain can't comprehend that. Like, I don't even know what a graph of that would look like. Honestly. Yeah. Log is fast though. Log is fast. But it's got like log times log, like, I don't know, like, right. Okay. The fact that somebody could prove that, like, blows my mind too. Okay. So there's one more. There's one more you guys need to know, which is order n login, which is called log-normal, logarithmic, what's the name of that? It's got a certain name. Big O Tires, that's funny. So I'm talking about, there's like a multiplier on there. Logarithmic, polylogarithmic, log star, linearithmic, or log linear. Linearithmic. There you go. Linearithmic. There you go. Linearithmic time. Don't worry, there will not be a vocabulary test on this. But basically, n log n is the provably fastest sort. So if you're going to be sorting random data, provably the fastest you can sort random data is in login time. Okay, and that's something you actually will need to know in this class. In login time is the fastest you can sort random data. Now, if you've done the Xi books, you'll know that there are things like radix sort and things like that, that if there are special properties of the data, then you can sort them faster, right? Like imagine you're sorting the results of coin flips, and so the only thing you're sorting are heads and tails results. Well, you don't need to actually do a sort per se. You can just go through it and count how many heads there are and how many tails there are, and then be like, all right, there were 50 heads and 20 tails or whatever, like that's a sort. If it's, if there's certain constraints on the data, then you can actually sort faster than in login. But if you're just talking about random data that's unconstrained, then in login is provably the fastest you can sort. You cannot sort a vector of size n faster than in login time, worst case. Okay. Quasi-linear. Yeah, there's a lot of cool names, and there's a lot of different complexity classes and things like that. These are the big ones. Okay. These are the big ones. This is what you need. And in addition to n squared, there's n cubed, n quarter, into this. And basically what those things will look like is this, right? Oops. If you have like a 5 times nested for loop, and COC is not complaining. That's interesting. Oh yeah, because they're shadowed. If you have something like this, this would be an order n to the 5th power algorithm, right? And the key here, if you haven't noticed, is you count how many nested for loops there are. If you have one for loop that goes from 0 to n, that's an order n algorithm. If you got a doubly nested for loop that each go to 0 to n, that's n squared. If it's triply nested, that's order n cubed. Quadruply nested, order n to the quarter. 5 times nested, pentuply nested, it's an order n to the 5. So when I was at CPPCon, I was taking an Uber, and Uber popped up a notification saying like, hey, it looks like you're at CPPCon. Would you like to take a test of your computer science knowledge? I was like, sure. That's weird. I've never seen Uber offer a multiple choice quiz before, but okay, And so we're like driving through the backcountry, actually, of the Seattle Renton area, actually, at the time, and I'm looking at my screen and it displays an algorithm like this. It's like, what is the running time of this algorithm? And I'm sitting there like counting the for loops, and the screen's like bouncing up and down like this, and there's a timer counting down. And I was like, and I got it right, obviously, because I teach this kind of stuff. And then I had a couple more questions along those lines. And then after, it's like, would you like a job at Uber? Press here, and a recruiter will contact you. Clearly, because you know Big O, you can get a job at Uber. And I was like, no, that's all right, man, thanks. But it was definitely amusing to me. It was in Python too, which was a little bit disconcerting to me because I'm mostly a C++ guy. So, yeah, Big O comes up all the time in job interviews. It comes up all the time just when you're talking to people. Okay. Must have detected my cell phone was at the convention center there. I think so, yeah. Or maybe they just figure if you're in the Seattle area, odds are pretty good you're a software engineer, because there's a lot of software engineers in Seattle. Amazon's based out of there. Boeing. Who are some of the other big names there? Microsoft. I think T-Mobile has a headquarters there. Apple, Bellevue. Yeah, I was staying in the Bellevue Hilton. Nice hotel. Okay. Starbucks. Yeah. There's just a lot of people there, and there was this CPPCon going on, and so they probably figured if there's a pickup from the convention center, they're a computer science person, they can try to recruit off them. Okay. So yeah, that's basically how that's the easiest way. You just count how many nested for loops there are, and these are the important ones here. These are the important ones. All right. So what homework assignment should we do next? So many options. What do you guys feel like doing? Do you guys feel like doing blackjack? You can do that in a pair if you like. You can do blackjack. We can do 1 more class-based assignment. I'm kind of almost done with classes, though.
A good one would be linked list if you're going to do class-based assignments.
We haven't taught linked lists yet. We could teach that on Friday, I guess. Just not give them any homework till Friday. I don't know if they like that. They want homework. They're hungry for homework.
Ooh, they're saying anything about bridges. Maybe a bridges assignment would be good. Dungeon Delve bridges is fun.
Yeah, I see Hazelton's asking for bridges. I mean, he's not technically in the class, but yeah, bridges Shakespeare. That's a good one. Let's see. All right. No, this one requires an unordered map.
Yeah, this one was actually pretty rough.
Yeah.
Shakespeare was surprisingly hard.
Man, so many different homeworks we can give. Can't believe how many homeworks we've made here over the years.
There's so much.
I know, right? All these that have these weird names, like 40, whatever, these are made by other professors. But,
Ooh, we're going to do quad tree at some point.
We could. You could have them do the RPG assignment.
That's what I was going to say. I could do RPG 41.
Yeah, I kind of want them to know some data structures, though, first for that.
Yeah.
So they can put their data structure knowledge to use. I think we'll just give them an easy one. What do you think?
Yeah. I mean, the last assignment wasn't that easy.
I'm going to pause the recording. We can talk about this. Okay, so yeah, I've been promising for a while to teach you guys TDD, so this seems like a good time. We're about to get into linked lists, but we got kind of an interlude right now where we're talking about Big O today. So this will be your next assignment, FizzBuzz TDD. And so how this works, sudo deploy homework, csci41, FizzBuzz underscore TDD. Yeah, okay. So cd FizzBuzz underscore TDD. Again, there's a make file, so use the make file to build it. Use make to build it, I should say. Make error no return statement, then main.cc line 13. Yeah, you should probably put something in there. All right, so for this assignment, you guys are going to write FizzBuzz. FizzBuzz is a classic job interview problem. How many people here have written FizzBuzz before? In Python, my assembly people have just done FizzBuzz as well. I don't know what FizzBuzz is. Okay, cool. So FizzBuzz is a classic job interview problem in computer science. It doesn't get you a job, but if you can't solve it, you don't get the job. Let's put it that way. It's used to screen out people that are utterly incompetent at computer science. Programming, I should say. Because computer science is actually more than programming. I should mention that. Computer science is math and engineering mixed together, stirred up. So what is FizzBuzz? So FizzBuzz is based on a drinking game. So I've actually played this game back when I was in college, and what you do is you pound on a table, and everybody counts on the pound. So you go 1, 2, 3, 4, and you go around. So if I said 1, then Blancas might say 2, and Muya might say 3, and Watkins might say 4, and you have to go on the beat. And if you miss the beat, you're out. You have to take a drink. But there's rules, okay? And the rules are what make it interesting, because as people drink more and they get more inebriated, it gets harder and harder to do the math and stay in time with the rhythm. So the rules are these. Instead of saying a number like 3, you say the word fizz, okay? And if a number is divisible by 5, instead of saying 5 or 10 or 15 or whatever, you say buzz. And if the number is divisible by 3 and 5, like 15, 30, 45, etc., then instead of saying fizz or buzz or the number, you say fizz buzz. And so it goes like this. 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz, 13, 14, 50. Dang it. Fizzbuzz. Right? And that's how it goes. And so you guys have to program that. So you're going to have to write a function called fizzbuzz that given an integer, 15, for example, you have to return what it should say. Fizzbuzz, fizzbuzz, or the number. Right? And so for this assignment, you should probably remember there is the toString function. So toString, if you toString 5, that'll print 5, right? Oops. So toString will be useful for you there. And here's the other thing. You have to write tests for your code. So TDD is a way of writing programs similar to what we've been doing in this class, right? Where you've got an input tester and things like that. Except for this assignment, you guys are going to make your own tests. So we're using something, I think we're using the gtest suite. Yeah, we're using the gtest suite here. And so what you do is you are going to create 3 sets of tests. You're going to create tests that are good, tests that are bad, and tests that are edge conditions. So what does that mean? So good tests would be like, you pass in you pass in a number like 33, which should be fizz, and maybe 50. And so basically what you do is you say, when fizzbuzz gets past 50, it should return buzz. That's what that line of code there means. Okay? And so you're creating tests for your own code. You're creating input tests for your own code. And then when you write your code, you can test your own code and see how many of the test cases you're passing. So the way that TDD, test-driven development, is the notion that you write your tests first. So rather than writing your code, then testing it later, what you guys should be doing is writing something like this. So writing fizzbuzz 1 should output 1, right? Or, 11, right? Should output 11, okay? And so you need to have good test coverage. You need to have at least one test case for every. Expect EQ means we are expecting, it's a macro, it's not a function. So expect EQ is part of the gtest suite. And what it does, it says we expect the result of fizzbuzz 11 to equal, EQ means equal, this string here. And if it doesn't equal it, then it will throw a red flag and say you failed that test. Okay? And so what you're going to have to do is you're going to have to generate enough tests here to cover all the different possibilities. Fizzbuzz, and the number. So you have to have at least 4 tests there, and I'd probably put in a few more. Okay? And I would make those before writing the function. Like you might stub this out, right, and just have it like return, that or something like that. You might want to just stub it out to begin with, so it'll compile, and then you want to write bad tests. So what does that mean? What is a bad test? Well, fizzbuzz takes a number between 1 and 100. So you might do something like expect the result of negative 50 to be error, right? So make sure you're handling all the error test cases, right? And then edge cases are when they're on the boundaries. So edge cases to test would be 0, 1, 99, 100, 101, and make sure that all the edge cases are actually behaving properly as well. Okay, so you're gonna have to write. I think it's like 5 test cases in each of these scenarios. The bad tests are going to be pretty easy to write. They're all going to be pretty samey. Just make sure you have some that are less than 1, some that are more than 100, and that's all you really need to do for the bad tests. And then for the edge tests, just do like 0, 1, 2, 99, 100, 101. Should basically be the same for everyone. And then for the good tests, just have good test coverage. So make sure you're testing a variety of numbers, and make sure you're testing fizz and buzz and fizzbuzz and numbers, and have some duplicates there. Okay.
Wait, did you start the stream again?
Did I start the stream again? Yes, I am recording again.
Okay, good. Just making sure.
Okay, and so when you run the code, you can just type test, and then it'll run the test suite on your own code. It'll tell you how many tests you passed. And so with TDD, what you do is you write the tests first, then you write your code, right? Or you write the test first, then you test your code, and you make sure you're failing all of the test cases. Like you actually want to start off failing every test case, because if you're passing test cases before you write code, there's something horribly wrong happening, right? Your test cases are bad, right? If you can pass a test case without writing any code, it's worrisome, right? So so you write your test cases, run the code, hit test. It'll look like this. Compile, run it, type test, and then it's going to tell you we are failing all the good tests. We are failure here. Edge tests are passing apparently, which because we don't have any in it. I don't think we have any test cases in edge cases right now. But good tests and bad tests are both failing, which is good. So in TDD, you do what's called red-green refactor. So you start off with red. Red means you fail your test case, and you write your code until you pass all of your test cases. So you start off failing everything, then you start writing your code, and as you start writing your code, it's like with my input tester, you start passing tests, and eventually, when you pass all of the test cases, you're done. Congratulations, your code is correct, and you've gone from red to green. And then there's usually one more pass called a refactor pass, where you sit down and clean up your code. Like usually when I submit something on like Code Wars or something like that, I finish it and then I look at it and I see if I can clean it up and simplify and make it look nicer and things like that. And then after you refactor it, you test it again to make sure you didn't break anything, because refactoring things can break things very easily. And so after you go red, you fail, you write the code, green, refactor it, you run it again and make sure it's still green. And once you do that, you're done. That's the assignment. Okay. So you got to write your own test cases. This is a very valuable thing. Don't rely on your professor to generate test cases for you, because I'm not going to be there when you're a professional, right? So make test cases and then write FizzBuzz. It's a pretty easy program to write. It's something they give you 15 minutes to do on a job interview, right? And you'd be surprised how many people fail it, right? So this will also give you some experience at passing a job interview, a very common job interview problem. It's not like you're not going to get the job if you can pass it, but if you can't write FizzBuzz in 15 minutes, you're not going to get the job. Not going to get the job. Will be due on Monday? Yeah, sure, that sounds fine. Okay. So get started on it now. If you have any questions on it, just ask in class on Wednesday or online. It's a really easy assignment. I've given this as like the first assignment in 41 before, or as the last assignment in 40. It's pretty straightforward. So nothing to do with classes, but it will teach you TDD, which is a very good skill to have. A lot of people do TDD these days in the professional world, so it'll be good for you. Okay, so that's it. So thank you guys, and I will see you on the flip side.